So hello everyone. In this video, we're gonna discuss about Huffman coding. So let's just get straight to the explanation part. Then I will come to this coding part. I will write the code as well. So first, now let's discuss how Huffman code works, how encoding decoding works. Okay. So I have my written down notes. So I will try to explain from this. So Huffman code again, it's a greedy algorithm. Okay. So this means an optimized space solution will be there for this. So what's its use? Why we use Huffman coding? Why we use this algorithm for coding? So its basic use is for text comparison or any sort of data compression method. Okay, let's say we want to reduce the size of some text data, so we will use Huffman coding there. Okay, so what's its advantage? Like why we use only Huffman coding? So its advantage is it's a lossless data compression method. As I've written down. So this means there will be no loss of data after this algorithm. So no loss of information. So that's why it is advised to use Huffman algorithm. So what are its application where we can see Huffman coding? Okay, so it's used in basically zipping files like we use pkzip, gzip, and all that. It's also used in fax method and all. So these are its application. Now let's get straight to the working of Huffman coding. So let me give you a short brief like how Huffman will work, how this algo will work. Basically, we will be creating a tree by calculating the frequency of each character of the string. Okay, we will be given a string of different characters. So we will create a tree by calculating its frequency. Okay, so now after we have created a tree, we will assign some unique code to retrieve the data back as we want to retrieve after it has been encoded. So for retrieving the data, we will be using some unique codes. Okay. So let's now get started with our working. So let's say we have a string s. Okay. I have written down this string. Okay, it has got 15 characters like B, C, double A, double D, double C, and like that. So this is our string. Let's say the total characters in the string are 15. Okay, as you can see, total characters are 15. So as we all know, 8 bits comprise of 1 byte, and that's the size of our char. So the total size of char for this will be 120 bits. Okay, 15 times 8. We have got 15 characters, 8 bits for each, 120 bits. That's our size. Okay. Now, before comparison, we know the size is 120 bits. Now, somewhat optimization is needed. We need to compress the size as we have got characters with frequency more than one. We have got several characters with a frequency more than one. So we know that Huffman coding can work in there. Each character has got more than one number, more than once in the string. Okay. So now let's calculate the frequency of each character from the above string. I've written this down. So basically, broadly, we have four characters in the above string: B, C, A, and D. Okay. So frequency of B is once. C occurs 6 times in the string. A occurs 5 times in the string, and D occurs 3 times in the string. Okay. So now comes the second step. We need to store them in a priority queue. And let's say this name is PQ. Now this will be stored in a min heap, the default priority queue. Why min heap? Because we want the minimum characters to appear at the beginning, okay, at the front. So we will make a priority queue implemented using a min heap, like so will be sorted in ascending order. Okay. So our priority queue will somewhat look like this in the beginning, like B, E, A, C with frequencies 1357 sorted in ascending order. So now comes our next step. Till here we have simply just made a priority queue in ascending order of the frequencies. Okay. So our next step. Okay. Now we will start with the making of tree. So for tree, my representation somewhat be like this. Like my node is n. So my node would look like the n. The left child will be the minimum frequency that will be picked up from the priority queue, and the right child will be the second minimum frequency that will again be picked out from the priority queue. Okay. So let's begin. And I have not told you just one thing. The node n, the value of node n will be the sum of these L and R. That minimum and second minimum will make the node n, that will be the sum of these two. So from above example, we had b occurring once, okay, and the next one occurring 3 times. So the sum 1 plus 3 makes the node n at the top, the left child the minimum one p. And the right child will be the second minimum 3. This is our first. Basically, it's again a tree in itself. So this is how it looks. So now we will update our priority queue. So 1 and 3 have been DQ from the priority queue. So now we will append the sum 4 as the front of our priority queue, and let's say we mark it as a star. This star is now basically the frequency size of B and D, and the star basically has this B and D as its internal nodes. Okay, so we have now A and C with frequency 5 and 6 respectively. So we will now repeat the above steps that we have done. So now our priority queue looks somewhat like this. 4 is at the beginning, 5 and 6. 4 has internal nodes B and D. So now the minimum one, 4, the second minimum is 5. So the sum will be 9 and the left child will be 4 and right child will be 5. Okay. Now updating the priority queue, I have 9. I have got 9 adding this. So 9 will be at the rear end. So now my tree will somewhat look like this. I'm appending the first tree. So 9 has got left child as 4, right child as 5, and this 4 is itself as 3. So 4 has got its left child as 1 and right child as 3. So till now, and note one thing, that after the tree has been completed, the leaf nodes will basically represent the frequency of those characters. So till now, we have done with B, D, A, and we are left over with C. And our priority queue somewhat looks like this at now. So we have 6 and 9 is the internal node. Now this internal node has B, D, and A. C is missing for this. So now sum of these two, 9 plus 6 gets to 15. So now we have 15 over there. So we are now done with our priority queue, and this is somewhat our final tree would look like. I am appended that. So 5, left child has 6, like the minimum one. The second minimum is 9. So 9 comes at the right, and this is basically we have done this in the previous steps. 9 has got 4 as its left child, 5 as its right child, 1 as its 4 has got 1 as its left child, and 3. So now we are done with our tree. Okay. So C has occurred maximum times. So then frequency is 6. So it's again a leaf node. 6 is a leaf node. It doesn't have any children further. So as I've told you that the leaf nodes will have those frequency of several characters, like different characters that we had in the string. So this is somewhat our tree looks like. So now let's move forward. Now the thing comes assigning the codes. Okay. As I told you that we will be assigning some unique codes. So to get the data back, to retrieve the data back, we need some code. Let's say I have 0 and 1. I will assign 0 to all the left childs and I will assign 1 to all the right child in the above tree. So 15 is the root. We won't assign anything to it. So 6 is the left child. I have assigned 0 to this. 9 is the right child. I have assigned 1 to this. Similarly, for different other characters frequency, I have assigned the values like 0, 0, and these were all left child, and 1, 1, these were all right child. Okay. So now listing codes. We will now list the code. How we will list the code? We have assigned some values. This was the main purpose of assigning the values. Like we will traverse for giving a code. We will traverse from the root, that is 15 over here, to the leaf node with the desired character. Like if we want to get a code for C, we will move from root 15 to the leaf C. Okay. So just a second. So our code will be like we will move. Let's say I want to get the code of C. Okay, we will move from 15 to C. So 0 occurs once, so my code will be 0. Okay, let's now get to the code of B. B for B, I will go to 9. That's 1. I want to reach the leaf node. Okay, 1. Then I will go to the left child, 0. Then I go again to the left child, 1. So 0. So 100 will be the code for B. Okay, so like that we will write code for each of the character. So now we have basically we have broadly four characters over there. I have listed down the codes, okay, their frequencies and their size. Now one thing you need to note that now the size is not as same as it was in the initial stage, like 8 bits. No, it is now reduced to the size of this code. Okay, like it has got 2 bits. Okay, so and again the final size will be decided on the frequency. So now we had four characters A, B, C, D. Okay, so that's now the total. I will not talk about the total space. Okay, that will be occupied. Initially, we had 120 bits. So now for storing the characters, there will be 32 bits. For storing the code, like for storing the frequency first, we have got 15 over here, 5 plus 1, 6, 12, and 3, 15. Over here, 15 bits for the frequencies, that the number of times the character is occurring. And for the size, now 5 times A occurs 5 times and its size has now reduced to 2 only. Like it has been encoded into this code 1 1 and each one consists of 1 bit. Now the total size is 2 bits only for this code. For this one it's 3 bit, for this one it's 1 bit, and for D it's again 3 bits. So my size has now reduced to 5 into 2 times 10 bits for A, 3 bits. It's a total size you need to know. And for C, my now total size is 6 bits, and for D, my total size is 9 bits. So this results in a total of 28 bits. Now the total size, like I've written this initially, we had 120 bits. Now the total size has reduced to 75 bits only, like 32 for storing the characters, 15 for storing the frequency, like number of times the character has occurred, and 28 is the code size of each character multiplied by their frequencies. Okay, 75 bits it has been now reduced. So and overall we have saved 25 to 20, 45 bits we have saved. So it's just on a small scale. When it comes to the larger application, like big size of data is space is saved basically. So this thing we need to note, like the character with maximum frequency will have the smallest code. Like for example, in the string we had C occurring the most number of times, that's 6, and its size is 0, like only 1 bit. Okay, so now comes the final step to decode this. Now again to decode it, like it's just the reverse how we encoded it. Okay, we have all these codes: C as 0, D as 101, A as 11, and B as 100. Now to be like, let's say we have given these codes. Now we want to get the character back. Now we don't know what's the character. We will now move from root to the leaf node, and we'll check what's the character over there. Like we have given a code 0 and now determine what's the character at code 0. So at code 0 we will go to the left subset. Okay, we have got 0 to the left and it's a leaf child. Okay, at the very beginning it's a leaf child. So C is the character. Just the opposite, like we encoded, we will decode it. Okay, traverse from the root to the leaf child using this code. We will get the character back. Okay, so this was all about Huffman coding. So now I will get to the coding part. I will write the code here. So before coding part, just have a look at the time complexity. How will be the time complexity for this one? So we have used a priority queue. Okay, as we all know, the time complexity for inserting a node in the priority queue is O log n. Okay, we have total n characters, so the time complexity for insertion will result in n log n. Okay, that's again not a very good but a decent time complexity considering the algorithm. For extraction, again this will be the same O of n log n. Okay, so now simply